Have you ever wondered how pilots control those massive machines we call airplanes? Now that's a question that sparks curiosity, right? To answer that, we need to delve into the world of flight control systems. Imagine you're in the cockpit of an airplane, surrounded by an array of dials, switches, and controls. It's a bit like being in the driver's seat of a car, only much more complex. Among these controls, you'll find the primary ones that pilots use to maneuver the aircraft: the control yoke or column and the rudder pedals. Let's start with the control yoke or column. It's similar to the steering wheel in your car, but it controls more than just left and right. When the pilot turns the yoke, it activates the ailerons on the wings. These are hinge sections that move in opposite directions. When one goes up, the other goes down. This causes the airplane to roll, tilting the wings and allowing the plane to turn. At the same time, pushing or pulling the yoke controls the elevators on the tail of the plane. These control surfaces move together, tilting up or down when the yoke is pushed or pulled. This changes the angle of the aircraft's nose, allowing it to climb or descend. Now let's talk about the rudder pedals. These are located at the pilot's feet and control the rudder on the tail of the plane. By pressing the right pedal, the rudder moves to the right, causing the nose of the plane to yaw or move to the right. Pressing the left pedal causes the opposite effect. So you see, flight control systems combine the actions of the yoke and the rudder pedals to control the ailerons, elevators, and rudder, giving the pilot control over the aircraft's movement. These are the primary controls, but how do they actually change the aircraft's direction? Well, that's a story for our next scene. Let's dive deeper into how these control surfaces work. First off, we have the ailerons located on the outer rear edge of each wing. When a pilot turns the yoke left or right, the ailerons respond by moving in opposite directions. If the left aileron is raised, the right one is lowered, and vice versa. This creates a difference in lift between the wings, which induces roll, allowing the aircraft to bank and turn. Next up, we have the elevators located on the rear edge of the horizontal tail section. They work in pairs, moving together when the pilot pushes or pulls the yoke. When the elevators are raised, the tail is pushed down and the nose of the aircraft is pitched up. Conversely, when the elevators are lowered, the tail rises and the nose is pitched down. This allows the aircraft to climb or descend. Lastly, we have the rudder. Positioned on the trailing edge of the vertical tail section, the rudder's primary function is to control yaw. When the pilot presses the left rudder pedal, the rudder moves left, pushing the tail to the right and yawing the nose to the left. And you guessed it, pressing the right pedal does the opposite. This side-to-side motion, or yaw, is used primarily for balancing forces in turns, but also helps in crosswind landings and takeoffs. Now you might be wondering, how does moving these control surfaces actually affect the aircraft? Well, it's all about manipulating the airflow around the aircraft. By changing the shape and position of the ailerons, elevators, and rudder, we can alter the direction and speed of the air flowing over them. This, in turn, changes the forces of lift and drag acting on the aircraft, allowing us to control its attitude, that is, its orientation relative to the horizon and trajectory. These control surfaces are like the steering wheel and pedals of a car, giving the pilot the ability to navigate the skies. They're a fundamental part of what makes flight possible. These control surfaces allow the pilot to manipulate the aircraft's attitude and trajectory. But how does the pilot know how to do this? Now let's examine how pilots use these controls in the cockpit. When we talk about flying, we often refer to the three main movements of an airplane: roll, pitch, and yaw. These are controlled by the pilot using the yoke and rudder pedals. Roll is controlled by turning or rolling the yoke left or right. This movement operates the ailerons on the wings, which work in opposite directions. When the yoke is rolled to the left aileron lifts up, and the right one drops down, causing the airplane to roll to the left. Pitch, on the other hand, is controlled by pushing or pulling the yoke forward or backward. This operates the elevators on the tail of the airplane. Pushing the yoke forward lowers the elevators, making the plane nose dive, while pulling it back raises the elevators, causing the plane to climb. Lastly, yaw is controlled by the rudder pedals. Pressing the left pedal moves the rudder to the left, causing the airplane to yaw or turn to the left, and vice versa for the right pedal. The rudder helps align the aircraft correctly during turns and assists with handling crosswinds during takeoff and landing. But it's not just about knowing which controls do what. The design of these controls, their placement, and how they feel to the pilot are crucial for precise handling of the airplane. Ergonomics play a big role in this. The controls need to be comfortable and intuitive to use, because in the heat of the moment, a pilot needs to be able to react without thinking. In real-world flying, these control inputs are often combined. For instance, during a turn, the pilot will roll the aircraft to one side using the yoke, use the rudder to align the aircraft and adjust the pitch to maintain altitude. Similarly, during climbs and descents, the pitch and power settings need to be adjusted simultaneously to maintain a stable flight. But what if we could make these controls even more reliable and precise? That's where the marvel of modern aviation technology comes in, but we'll delve into that in the next scene. Welcome to the future of flight control systems, fly-by-wire and automation. Imagine an orchestra, where each musician plays their part to create a symphony. In the world of aviation, the engineers are the musicians, and the symphony they create is the intricate system of fly-by-wire technology. Diving into the backstage of an aircraft manufacturing plant, you'll find engineers meticulously working on the fly-by-wire control system. This is not your everyday mechanical linkage. The fly-by-wire control system is the backbone of modern aircraft, transmitting pilot inputs to the aircraft's hydraulic actuators through electrical signals rather than mechanical connections. But why does this matter? Let's break it down. The fly-by-wire system introduces redundancy, meaning there are multiple backup systems in place. So if one system fails, another one is ready to take over. This significantly improves the reliability of the aircraft, ensuring a safer flight for everyone on board. Moreover, this system dramatically reduces control forces. Think about it, a pilot doesn't need to exert as much physical effort to control a massive aircraft. Now it's more about precise finger movements and less about brute strength. This not only makes the pilot's job easier, but also allows for more precise control of the aircraft. Beyond that, fly-by-wire technology enables something called flight envelope protection. This is a fancy way of saying that the system prevents the aircraft from entering into potentially dangerous flight conditions. It's like an invisible shield protecting the aircraft from making maneuvers that could put it at risk. All these features combined create a control system that is reliable, efficient, and safe. It's a system that is continually evolving and improving, pushing the boundaries of what is possible in aviation. But how does this technology actually work in a real flight scenario? Let's see how these advanced control systems are implemented in real flight scenarios. Consider the massive Airbus or Boeing jets that dominate our skies. Their flight control architecture is a marvel of engineering, incorporating the latest in fly-by-wire technology. These systems are designed to make flying safer, more efficient, and more convenient for pilots and passengers alike. Take autopilot, for example. This isn't just about making a pilot's job easier, it's about precision. Autopilot can maintain a set course and altitude with a level of accuracy that surpasses human capabilities, especially during long-haul flights. Then there's auto thrust. This technology adjusts the power of the engines to maintain a set speed or climb rate, optimizing fuel efficiency and ensuring a smooth ride. Flight management systems are another crucial component. They're like the brain of the aircraft, using inputs from various sensors and databases to plan and control the flight path. They take into account factors like weather conditions, air traffic, and fuel consumption, making decisions that help ensure a safe and efficient flight. Now let's imagine a typical automated landing sequence. As the aircraft approaches the airport, the flight management system communicates with the autopilot, adjusting the aircraft's speed, descent rate, and direction. The auto thrust system adjusts the engine power as needed, while the fly-by-wire system manipulates the ailerons, elevators, and rudder to keep the aircraft on the optimal glide path. All these systems work in harmony, guided by complex algorithms and high-speed processors. But don't think for a second that pilots are just sitting back and watching the show. They're constantly monitoring these systems, ready to intervene if necessary. Automation aids pilots, but it doesn't replace them. Pilots bring a level of understanding and intuition that no machine can match. They're the ones who make the final decisions in unexpected situations, drawing on their training and experience. As you can see, flight control systems are a fascinating blend of human skill and cutting-edge technology, ensuring that every flight we take is as safe and smooth as possible.